So without further ado, we will welcome Professor Cal Riding to give a presentation. And the next three speakers, our co-moderator, Dr. Alvaro Paul, will introduce them. Thank you very much.
All right, thanks. All right, so this is a presentation. I'm going to talk a little bit about fiber alignment in the UHPC test when you're actually testing for qualification or quality control. Now, just to set expectations, maybe I have more questions than answers in this talk, but we'll go ahead and bring you on this journey. All right, so let's talk a little bit about what you get. So if you were to test ultra high performance concrete, what sets it apart from our normal strength concrete is you get the tensile strength and the ductility that out of this that you don't get out of normal strength concrete that doesn't have fibers in it. So we get that ductility and that tensile strength. You need to be able to measure it in order to be able to take advantage of these properties in your UHPC members. So that's something that we're, as an industry, we need. There's just been adopted in the last couple of years the direct tension test that was developed, great work at Federal Highway Administration to do that for qualification. But one of the issues that you have is that this test, there are very few labs that can run it. Although the number of labs is growing by the day of labs that can run it, but it still has its challenges for running it for quality control. So if we're thinking about tests that we want to run for qualification or quality control, one of the things I would propose is they don't necessarily need to be the same test that you run for each test. We do that a lot in our construction, where we have tests that we run for qualification and then ones that we run for quality control that are different, that have different purposes maybe. So think that in mind. What's your purpose of running the test? So that's maybe the takeaway that I'd love to have here is, what's your objective for your tensile testing? If you can keep that in mind when you are setting out to design your test and to select your test, then you have a little bit better chance of actually hitting your target. And sometimes we forget that. Okay, so what are we trying to demonstrate? Maybe for our ideal quality control test, we'd want it to accurately characterize the tensile strength. We'd also want a measure of ductility or toughness. We want a measure of what's that response going to be after you get cracking, so we can see the benefits of the fibers. We want something that can also be done with equipment that's commonly available. The test equipment out there is quite expensive. Although there's been some innovations to bring the cost down, it's not just the equipment, it's the training and the expertise that's needed to run some of these tests is quite high. So it needs to be simple to perform, easy for technicians, and it needs to be, above all, also repeatable. So these are if you were to dream up your ideal QC test, that would be what we would want. But maybe you have to compromise in some areas. Keep in mind that for many UHPC projects over the last 5 years, our tensile test that we've been running is actually a compressive strength test. So they haven't been doing quality control tests on the tensile properties, and so that's something to keep in mind, is even if it's not an ideal test, is it better than what we're doing right now, and does it help us encourage better quality control from the contractors? Okay, so there's really 3 different types of tests that you can have for measuring the tensile properties of concrete. You can have some sort of direct tension test, and there's a number of flavors of this test out there in the literature, and the best well-known is the one that was developed by the Federal Highway Administration and now is an AASHTO test method. And it's a good test. It provides a lot of good information. It gives you a stress strain curve that you can actually use in design without having to do inverse analysis. And but it can have a high proportion of failed tests, especially depending on the experience of the laboratory and some of the other properties in your sample. But it can also have some preferential fiber orientation depending on how the samples are made. And we'll talk about that in a second. The second type of test that you can use for measuring the tensile properties of concrete is a flexural test. And this is basically a bending test where you have compression on the top part of your concrete, tension in your bottom part. Pretty simple concept in theory, but in practice, it's not necessarily the easiest to do. One flavor of this test is the ASTM C1609 test, and there are other tests out there in Europe, the CMOD test or other tests that have been developed. But the principle is still the same, where you have a tensile strain on the bottom part of your beam, and you're trying to then use the force deflection curve to then either get some sort of stress strain curve out of it by that test. So there is some sort of analysis that needs used in this test, or in these categories of tests. Probably the third category is a splitting type of test. So you have, for instance, splitting tensile test is the most widely used and known test for tensile strength. Another a type of test that's used is a double punch test, where you basically have two punches on the top and bottom of your concrete, and as you compress the concrete, you form cones of failure underneath those, and as you do that, then you start to split or wedge open your sample. Barcelona, or in Spain, they have a standardized method for this test, and it can give post-cracking data. It does not give strain data, and it's not going to give you a stress strain curve, but it is a test method out there as well. Okay, so let's look at these. If we were to look at these, probably the most common of each category are the ones that we looked at. You have the 1609 flexure test, you have a direct tension test, and then we've simplified the double punch test as a method as well, and I'll get into that in just a second. Okay, so if you look at placement effects, the first thing we wanted to do was we wanted to look at what's the effects of the placement location. This is a question that's had in the test method. You're supposed to place the concrete from one end of the beam, and the concrete flows to the other end of the beam and fills the samples that way. Again, when you're designing a test, you need to think about, what am I trying to replicate? Am I trying to replicate the fiber orientation and distribution that's actually in the concrete that I expect to place, or am I trying to come up with a test that's repeatable, that will represent the concrete as a standard method that is done under standard conditions but may not represent what's in the actual concrete. So that was the method that was chosen for this, is to fill it from one end and let it flow. And then we compared that to filling it from the center and letting it flow to the ends, and we found no statistical difference with doing that. One of the concerns that was there is what can happen during placement, and I think our previous speaker did a great job of illustrating this, but if you have concrete that flows as it shears in that shear zone, you're going to get fiber alignment that occurs, and anywhere there's shear, you get that fiber alignment and preferential orientation as you move away from where the concrete is placed. Additionally, if you don't have great rheological properties, you can get settlement and have dispersion issues. So we wanted to look at our samples, what's happening on the shear zone as that concrete flows along your 2-inch prism. It's a 2-inch by 2-inch by 17-inch prism in this sample. So we took a beam and did computed tomography scanning on it to look at your beam fiber orientation, and what you see, if you look at the center, you do have some fiber orientation in the center, but near the edge, you definitely have fibers that are oriented near the edge, and this is a well-known effect. This is something in the French code describes for flexural tests, that you get fiber orientation on the edges of your sample because you're shearing the concrete, and fibers that would normally be randomly oriented, that would normally poke out of the mold if they're truly randomly oriented, and they can't do that. And so as they shear, they get oriented and turned inward. And so this is a real effect that we can see happens with these samples. So we looked at it, and if you take the French method for taking this into account, if you say, for instance, apply a correction factor to the edge of your beams where they're formed edges, and you apply a 1.2 multiplier to the area there when you're calculating the stresses, it ends up being about a 6.8% difference that you would have that we're potentially overstating the tensile strength by about 6.8% when we have direct tension tests. Additionally, you could be, and it's probably a slight effect, it may not affect the results in practice, but if that's the case, you may also have the case where you have more fibers aligned on the bottom than you may have on the top, where it's a formed surface, and you could actually have samples where you get a little bit of non-uniform tensile strength across the member, and it could cause a little bit of bending in the sample. It's probably not significant enough, but it's something that could be there. So again, this is I'm not trying to say that we shouldn't run this test. I think it's a great test, and it does a lot of good things where it's a consistent test, where if you place it on the end, it seems to be consistent, but we need to understand that what are we measuring, and that what we're measuring it may not be the exact thing that we're having in the concrete when we place it, but that's not the worst thing in the world either, too, as long as we understand that and recognize that. So in this case, using half the fiber length around the perimeter. Okay, so we also looked at a test that we helped simplify. It's now been standardized as a Florida Department of Transportation test method. It's a simplified version of the double punch test, where you have a 6-inch diameter cylinder and 6-inch tall that you place in compression, and it splits. You can see the splits on the bottom sample. And in this case, we simplified it so you can use it in an open loop displacement control. I know that the Fiber Reinforcement Committee is probably having a heart attack when I say that right now, but that's okay. It's meant to be a simple quality control test. So if we look at it, we've done some testing with this to look at the displacement rate before and after cracking. And it's pretty repeatable, and we did a ruggedness study that showed that it didn't have a statistically significant effect on the results. Okay, so in this simplification, you do this test. The traditional method, the method that was developed in Spain, is you use an extensometer around the diameter of the cylinder. You have 2 punches, and as you squeeze the sample, you measure the barreling or the increase of the diameter. That's very expensive equipment, and that's something that I can just see many labs not getting right for quality control. And so we simplified it first by, let's measure the displacement of the crossheads in a open loop, just regular compression machine, and then simplified it even further by, okay, if that works, we can just take measurements where you have a dial gauge, and at certain intervals of displacement of the crosshead, you write down the strength, and you can get a plot of it. And we found that when you do that, if you compare the continuous data to these points, it ends up being about a 1%, 1.5% difference that you get by simplifying it and doing it manually than doing the continuous data. Is that acceptable? Well, for quality control, if we're able to democratize this test and make it more accessible to people, maybe that's an acceptable trade-off. Okay, so by taking these values every 0.025 inches, that's the trade-off that we had. We did a ruggedness study, and the thing that we found from this is the most significant factor was how you make the sample. And that's probably true of most of our tensile property tests that we have for concrete. That's probably our most significant thing. We tested different machines. That didn't really seem to make a difference, not statistically significant, but how you make it really is. And so when we did this ruggedness study, what we found is if you scoop the sample, what you end up doing is you're creating many layers on the sample. And these end up causing preferential orientation when you make them. When you make the samples, you end up getting very, very high tensile strengths when you do that, whereas if you fill it with a bucket just in one placement or pour, you get a little bit more random orientation that you have there. So, and we did computer tomography to examine that, and you see that we had more horizontal fibers, a lot more horizontal fibers when we placed it by hand with a scoop in layers, basically, than a bucket filled. Another thing that you see is from these scans is that you end up getting a lot of swirling patterns of fibers. We like to think of our UHPC as having this random orientation or preferred orientation when everything lines up, but that's not how things are in reality. You end up having patterns of how the concrete flows, and how it flows, you get swirled patterns of how it went in and then it stopped flowing, and how it sheared in there. When you take cores out of these samples, this is the type of thing you see quite often, as these swirls of patterns of fiber distribution. Okay. So we did a round robin study and looked at 3 different materials and characterized with 3 different materials at, I believe it was 10 or 11 laboratories, the round robin study here, and we found that when we did that, the peak stress and the toughness, these are the types of variances that you saw. Pretty reasonable. They matched up pretty good with what the 1609 has. And again, remember, this is a test that was run at a bunch of different labs and we trained undergraduates in our lab to run it, high school level education, and they were able to run it. Okay, so here's the one thing that we did see a high variance with was material C, and it's because of the number of samples we were making with this. We increased our number of samples that we were making, and we saw a trend as we placed the concrete. You saw this upward trend of the strength as we went on. We think that the last 5 or 6 samples that we had ended up having much higher strength because you're scraping more of the bottom of the barrel of the mixer, and so we think that's what caused the higher variance on this. Okay, so now if we have a test, it's not perfect. We may or may not get to a perfect test for quality control, but we shouldn't let that stop us from doing good construction. And so in that case, then what we can do, one option is to do a more expensive but better test, like the direct tension at qualification, get the stress strain properties that we want for design and ensure that that material is going to do what we want, and then accompany it with the cheaper test that's easier to run and do a correlation to it, and to get properties so that it's possible each material may have its own quality control requirements. But what we see when we compare the direct tension test to, for instance, a flexural 1609 test, you can get very good correlations with the same materials. And we looked at with direct tension versus our double punch, you can get decent results there on the tensile strength, and with the double punch toughness versus the direct tensile toughness, or the stress at 0.005 strain. So it is possible, we think, to get some sort of correlation during the qualification stage to be able to give you a test that's much easier to run. Not perfect, it's not going to be, but maybe not perfect is better than what we are doing right now, which is nothing in many cases. So we can't let the perfect be the enemy of good. But again, I don't have all the answers to what the perfect test is. We haven't met our ideal test requirements here, but maybe some questions for you to think about. And certainly when we were making these samples, how you make them is definitely the most important variable that we saw. Okay, so we get preferential orientation at the edges of our samples. We're able to look at this double punch test for the repeatability with our round robin study, and correlation is one possible way. There needs to be more work done in this area, but it's one possibility. Okay.